So this video is going to focus on how to draw a potential energy diagram for an exothermic and an endothermic reaction. So let's go ahead and learn how it is done. So what is a potential energy diagram? Actually, a potential energy diagram tells us the change in energy of a reaction as the reaction progresses. So with the reaction progress on the x-axis and potential energy on the y-axis, the energy diagram is drawn over there. R written over there is for the reactant and P is there for the products. It's not possible for the reaction to go directly from R to P. It has to pass through an elevation. We call that as a hill also, as shown by the arrow over there, to reach the product. This elevation or this energy which a reaction has to cross before it reaches a product is called as the activation energy. And the state of the reaction at the activation energy is called as the transition state. It's neither the product nor the reactant. So the bonds of the reactants are getting weaker, and some bonds with the products are also formed. That happens in the transition state. So now you can see that the product is at a higher level than the reactant. Such reactions in which product is at the higher level than the reactant, we call it as an endothermic reaction. And the difference in the energy between the product and the reactant is called as delta H. So delta H is EP minus ER. Since as the product is at a higher energy, the value of delta H will be positive. So for an endothermic reaction, these are the things which you should notice. Product will be at a higher energy than the reactant, and the value of delta H will be positive. Now similarly, we have a potential energy diagram for an exothermic reaction. So if you look at it carefully, here also it has to cross through a hill or a minimum energy called as the activation energy before it reaches the product. But the point to be noted over here is the products are at a lower energy than the reactant, and hence when we calculate the value of delta H, the energy of the product being lower, the value of EP minus ER will be negative, and these are the characteristics of an exothermic reaction. Product at a lower energy level, and hence delta H will be negative. So keep it in mind, endothermic delta H is positive, exothermic delta H is negative. This is what we have been learning from the previous chapters also, and our potential energy diagram also supports it. The new factor which you learnt in this diagram is the EA, the activation energy, which is the minimum energy a reaction has to pass through. It's a hill, and before it reaches the product. And the speed of the reaction also depends on the activation energy. If a reaction has a higher activation energy, it will be slow. If a reaction has a lower activation energy, it will cross the hill faster and it will be fast. A reaction has the following energies. Products are 52 kilojoules, reactant 34 kilojoules, and the activation energy is 74 kilojoules. You are asked to draw a potential energy diagram and predict if the reaction is exothermic or endothermic, and calculate delta H also. So when I look at the values of the energies of products and the reactants, you realize that reactants are at a lower energy than the products, and hence when the potential energy diagram will look as shown over there. And the reactants, you can see it's shown at a lower energy than the products. And this is an endothermic reaction, because this is the potential energy diagram for an endothermic reaction. Now the activation energy EA 74 kilojoules is the height of the curve as shown over there. Now what have they asked us to calculate? They have asked us to calculate the value of delta H, and delta H we know is EP minus ER. And substituting the values of the energies of the product and the reactant I get the value of delta H, and it's a positive value. So this indicates and supports that it is an endothermic reaction. From the diagram given below, predict activation energy delta H and if the reaction is exothermic or endothermic. So first observe the diagram. You can see that the reaction are at a higher energy than the products, and such a situation leads to an exothermic reaction. And then, as always, to calculate the delta H, it is EP minus ER. So that means it is 27 minus 38, and that gives you a value of negative 11 kilojoules. So being an exothermic reaction, the value of delta H comes out as negative. The reaction A plus 2B giving you C plus 3D has an activation energy of 150 kilojoules and the value of delta H is 60 kilojoules. So now they are asking whether the reaction is exothermic or endothermic. You have to draw a potential energy diagram for this reaction, and the third one is a little different. Calculate the activation energy for the reverse reaction. Calculate the delta H for the reverse reaction. Now, the first one, delta H is positive. Therefore, it's an endothermic reaction. And hence, the potential energy diagram for this reaction will look as shown over there, with the reactant at the lower energy than the product. So, this is easy up to this. Now, the next part is, in the potential energy diagram, I have shown where the activation energy is also there, and the difference delta H, the difference between the reactant and product is also shown there. Now the next question, calculate the activation energy for the reverse reaction, and you can see that the activation, the hill the product has to climb to reach the reactant is smaller than the one which a reactant climbs before it reaches the product, and the given activation energy is for the forward reaction. Therefore, the activation energy for the reverse reaction will be equal to E forward minus the delta H, because that amount of delta H now it is decreased from the activation energy, and hence the reverse activation energy is equal to 150 minus 60, that comes as 90 kilojoules. Now the last question, calculate the delta H for the reverse reaction. Forward reaction is endothermic, hence the reverse reaction will be exothermic, and delta H reverse, because delta H is an intensive property, it doesn't change just with the path or the direction. The only thing it changes will be the sign. Therefore, delta H reverse will be equal to negative 60 kilojoules. So the important stuff in this question is understand the answer to question number 3 clearly. If you look at the figure, it will be very clear that the difference in the how the activation energy changes from the reverse reaction to the forward reaction.